Hello students, myself Antara Vishal from ECE Department of Guru Nanak Institute of Technology, and today is my lecture number 80, and the topic is under module 2. Module 2 is junction physics in semiconductor device, and today's topics are metal semiconductor contacts, and there are some course outcome, there are 4 course outcome of this subject, and the first one is able to understand the energy band diagram, charge carrier transport phenomenon, and the recombination generation process of different types of semiconductor materials. Second course outcome is to able to understand the characteristics and current flow of semiconductor devices like BJT, JFET, MOSFET, and metal semiconductor junction and heterojunction devices. Third course outcome, that is able to analyze the design parameters of MOSFET, that is channel length and width, depletion width, surface field and potential, port resistance, transconductance, equivalent circuits, amplification factors, capacitances, noise margins, scaling, and short channel effects of MOSFET. And the fourth course outcome is to able to illustrate rectifying properties of different types of junction diode, importance of reverse current in solar cell and LED. Now, today's topic is metal semiconductor contact, and there in course outcome, that is the second course outcome. In second course outcome, that is metal semiconductor junction and heterojunction devices, means today's topic's course outcome is the second course outcome. Now, here we will discuss the topic under module 2. Today's topic is under module 2. Under module 2, the topic is the junction physics in semiconductor device, and under this module there are different topics, that is semiconductor junction, that is mono junction pattern, which we have already discussed. Under this part, we have discussed about homo junction, that is semiconductor junction. What about the energy band diagram, the depletion region, the width, the capacitance, and if the current, if the junction is forward bias and reverse bias, what is the current components, and derivation of the inbuilt potential, that is built-in potential barrier, depletion with junction capacitance, character diode. What about character details on character diode, and then Zener breakdown principle, Zener and average breakdown. Also, there are 2 types of breakdown, and the static and dynamic resistance of rectifier diode, and that is the first part. And then next part is about solar cell and LED, which we have already discussed. Under this section, what is solar cell, how it works, and what is the conversion efficiency and field factor, already we have discussed. Also we have discussed about LED, that is light emitting diode. Next part is semiconductor junction heterojunction. Under this topic, there are energy band diagram, classification of heterojunction, 2D electron gas, and isotype and anisotropic about isotopic type and anisotropic type heterojunction, their IV characteristics and theoretical problems, which we have already discussed in previous class. Okay. Now, in previous lecture. Okay. Now, today's lecture is on metal semiconductor junction. Under this section, there are metal semiconductor contact. There are two types of ohmic and non-ohmic contact, and Schottky diode. That is application. And all total lectures of under this module is 10. Okay. Now let's start. What is metal semiconductor junction? The metal semiconductor contact. This is an important component. This is an important component in the performance of the most semiconductor devices in the solid state. Okay. Now, in metal semiconductor, that is image junction, is that if metal and the semiconductor material are contacted closely. Okay. Basically, there are two types of metal semiconductor contacts that are widely used in semiconductor devices. First one is a rectifying Schottky diode, and another one is non-rectifying ohmic contact. Okay. Now, this is the introduction, that the principle of forming different types of the metal semiconductor contact is the mismatch of the energy between metal and the semiconductor material. Which is due to the difference in work function. Now, there is figure 1 here. From figure 1, we can say that we can see that the energy band diagram after the contact is made. Okay. Now, in the figure, you can see that the vacuum level, that is E0, vacuum level, that is E0, the minimum energy needed to release an electron from the material is used to align the metal and the semiconductor together. And the work function phi, which is defined as the energy difference between the Fermi energy and the vacuum level. That for the metal, that is phi m, that is the work function. Work function means Fermi, the energy difference between the Fermi energy and the vacuum level. Now, there comes to the electron affinity, that is chi. That is electron affinity. It is defined as the required energy for moving an electron from the vacuum level to the conduction band. From electron affinity is the energy required for moving an electron from the vacuum level to the conduction band. Okay, that is chi equal to within bracket E0 minus EC FB at surface. Now, when a metal and a semiconductor material are brought together, an instant ideal metal semiconductor contact is formed. Now, if there is no electron movement during the contacting process, the Venn diagram for the contact will be as in figure 1, where the mismatch for the inner Fermi energy, that is EFA, in the metal and the Fermi energy in the semiconductor, that is EF. Now, for the ideal metal semiconductor contact, several assumptions are made. What are the assumptions? That the metal and the semiconductor are contacted intimately, which means that there is no oxide or change layer between the contact on the atomic scale. Okay. Next, second one is we can say that no intermixing and interdiffusion between the metal and the semiconductor. And there is another point, that is there are no impurities at the metal semiconductor interface. Now, the electron affinity chi and the metal work function, that is phi a, are invariant fundamental properties of the they are the fundamental properties that remain unaffected. Okay. Now by the contacting process. Okay. However, the work function of semiconductor is related with the electron affinity, the conduction band, and the Fermi energy. Now, that is phi s equal to chi plus EC minus EF at FP. And here that chi equal to, already you know that chi equal to chi equal to E0 minus EF. Now, however, the situation in figure 1 are not in equilibrium condition, since the Fermi energy in the metal is not aligned with the Fermi energy in semiconductor. Here, this is the Fermi energy of metal, and here this is the Fermi energy of semiconductor. They are not aligned. Now, Therefore, the electrons will keep transferring between the semiconductor and the metal until EF is aligned. Now, therefore, in this figure you can see that is the Fermi energy of metal, and that is the also here also there is a difference, and here also there is a difference between Fermi energy of metal and Fermi energy of n-type semiconductor. Now the electron will keep transferring between the semiconductor and the metal until the EF is aligned, which would cause a formation of depletion region between the contact. With different characteristics of the metal semiconductor interface, two types of metal semiconductor contact will be formed: the rectifying Schottky diode and the omic contact. First one was rectifying Schottky diode, and the second one is the omic contact. Now, what about Schottky barrier contact? Schottky barrier contact, which refers to the metal semiconductor contact. Here, a large potential barrier height is formed when the P type P when the Fermi energy of the metal and the semiconductor are aligned together. The period height, that is phi g, is defined as the energy difference. Here phi b is defined as the energy difference between the band edge with majority carriers and the Fermi energy of the metal. Chi equal to E0 minus EL. Now the condition is under equilibrium condition, that is when the applied bias V equal to bias voltage, that is V equal to 0. Now first consider the case where phi A greater than phi S, that is work function of metal is greater than work function of semiconductor. Here electrons will transfer from the semiconductor to the metal due to the greater energy, and it continues till the equilibrium condition is established. Now the net loss of electrons, which creates a negative charge in the metal and a positive charge in the semiconductor, and that results a depletion region and a growing barrier at the semiconductor surface. That means the equilibrium band structure for a metal and the n-type of semiconductor is shown in figure 2. This is the metal, and that is phi B, and this is n-type semiconductor, and here are the barrier. Now the surface potential energy barrier, that is phi B, the primary characteristics, which is the primary characteristics of a Schottky barrier, is characterized by the Schottky barrier height, and that is the function of the metal and the semiconductor. Now phi B, you can write that phi B equal to phi M minus chi for n-type of semiconductor, and phi B equal to E G by Q plus chi minus phi M for P type of semiconductor. Now the barrier results a high resistance. When there is even a small applied voltage, since the potential barrier height could be governed by the voltage bias, and that has a significant influence of the electrical current which is flowing through the barrier. And the effect of forward bias and reverse bias are also there is the effect of forward bias and reverse bias. Now, what is the effect of biasing? First, if we consider that phi m greater than phi s, then the metal semiconductor contact contact, then a current, that is I, will be formed if there is an applied voltage, that is VA, on the metal, and here that is the VA, and the semiconductor is connected to be grounded. Okay, that is shown in figure 3. Here are the current direction of the current, that is VA. Here this is metal and this is N type of semiconductor. And the current is defined to be positive when it flows from the metal to the semiconductor. Now, if we consider the forward biasing, then under a forward biasing condition, that is VA greater than 0, the operation of a metal semiconductor junction is shown in figure 4. The Fermi energy of metal becomes lower than the Fermi energy in the semiconductor, that is EF, which results a reduction of the potential barrier phi b. Here, as the barrier potential is reduced, then the barrier height, that is phi, also the potential barrier, that is phi b, across the semiconductor is reduced. Now it will be much easier for electron to pass over the barrier. That makes the electrons diffuse much easier from semiconductor to the metal. Now, therefore, as the VA, if we increase VA, then the current will increase rapidly. Then more electrons will be able to overcome the surface barrier without coming back, corresponds to the opposite direction of the current. There will be more electrons diffuse from the semiconductor towards the metal. Then the electrons which are drifting into the semiconductor. A positive current will be generated across the metal semiconductor junction. Now, if the there is reverse biasing. Now, with a negative applied bias on the metal, that is V less than 0, the operation of metal semiconductor junction is shown in figure 5. The Fermi energy of metal becomes higher than the Fermi energy of the semiconductor. That means that increasing of the barrier height, that results the increasing of a barrier height or barrier potential across the metal semiconductor junction. The large barrier will block the diffusion of electrons from the semiconductor to the metal. Now, under a small reverse bias, only a small amount of electrons in the metal may be able to overcome the potential barrier. Okay. Therefore, the current I will become a small constant at reverse bias condition, okay, which is characterized as a rectifying behavior. Now, in general, the current flowing through the Schottky contact can be defined with the applied voltage, and which is very similar to those PN junction diode. And the IV expression, that is current voltage expression, is I equal to I0 into e to the power QVA by KT minus 1, where I0 is saturated current. And this is the IV characteristics, which is shown in figure 6. And here, under a forward bias, that is VA, when VA greater than 0, the forward bias exceeds then a few kT by Q volts, the current will be dominated by the exponential term. For the reverse bias, that is when VA less than 0, when the reverse bias greater than a few kT by Q volts, then the exponential term will be neglected. That results a small saturated current, that is I equal to minus I0, and this is the IV characteristics of Schottky diode. Now, next is what is ohmic contact. Now, all metal semiconductor, not all the metal semiconductor contact can perform as a rectifying Schottky diode. There are some, there is no potential barrier is formed. Because if the Schottky that metal semiconductor contact is not rectifying Schottky diode, then there is no potential barrier is formed. Okay. Now, under this condition, when the current can be conducted in both direction of the metal semiconductor contact, the contact is defined as the ohmic contact. That type of contact is ohmic contact. Now, an ideal ohmic contact is a low resistance and non-rectifying junction with no potential exists between the metal and semiconductor interface. Now, consider the case in figure 1b. In this condition, the metal semiconductor contact with phi m less than phi s, electron will transfer from the metal to the semiconductor due to their low energy, which will cause the Fermi level in semiconductor move up until the equilibrium state is established. Okay. Now, the band diagram under equilibrium state is shown in figure in this figure, that is 7a. Here this is metal, this is N type of semiconductor, that is EFM, that is metal, Fermi level for metal, and here this is EF, that is Fermi level of N type of semiconductor. Now, as there is no barrier structure for electron flow from semiconductor to metal, even a very small forward bias voltage, that is VA, greater than 0 will rise a large forward bias current. When there is an applied reverse bias voltage, a small potential barrier is formed for electron flow from metal to semiconductor. However, the small barrier will eventually vanish when the reverse bias voltage becomes larger. Okay. Now there is a large reverse current flow when V less than 0, and the IV characteristics is shown in figure 7b. Now, we can say that the ohmic contact behaves like a linear current volts curve that follows the Ohm's law in both forward and reverse bias condition, which is not matched with Schottky contact. Okay. Now, at the conclusion, here you can see that for a metal and N type of semiconductor, a rectifying Schottky contact is formed when Fm greater than phi, phi m greater than phi s, and an ohmic contact is formed when phi m less than phi s. Similarly, for a metal and P type of semiconductor, this was for N type of semiconductor. But if we consider a metal and P type of semiconductor, then if phi m greater than phi s, then the metal semiconductor contact will be rectifying Schottky contact when Fm less than Fs, and ohmic contact will be formed when Fm greater than phi m greater than phi s, and this is shown in the table. Till now, today we have discussed about what is metal semiconductor junction. Under this, there are two types of contact, that is rectifying Schottky diode and non-rectifying ohmic contact. We have discussed about what is Schottky contact, Schottky barrier contact, and there are three conditions, that is there are two types of biasing, for under forward biasing and under reverse biasing. What are the effects which we have discussed, and the IV characteristics of Schottky diode, which is shown in figure. And next is ohmic contact. Here the band diagram is shown in the figure, and also the IV characteristics is shown, and which is similar to the we can say that that is similar to that IV curve follows the Ohm's law, both in forward and reverse bias condition. And at the conclusion, if phi m greater than phi s, and if the one side if the junction is formed between metal and the N type of semiconductor, then if phi m greater than phi s, then that will be act as a rectifying contact, and metal and p-type semiconductor is considered, then if 5 times 5s, then that is moving contact. That will form a moving contact. And in case of 5m less than 5s, in that condition, for metal and n-type semiconductor, it will be a moving contact, and for p-type, for metal and p-type of semiconductor, it will be rectified contact. And that's all for today.